All right, it is finally time. Today we get to learn how to make our own functions. It's going to be great. It is going to take us a few lectures to get through all these slides, but we are ready. We're ready to make our first functions ourselves. All right, because the whole point of functions, at least one, is to split stuff up. Because I can imagine that you are feeling this way right now, right? You make big long main functions at the moment. That is where you can only put your code right now. You are forced to put so many things in your main function. Stuff like that, but more lines to do some other thing, more lines to do some third thing, and then of course your return 0 once you make it to the bottom after all that. But usually your program can be broken down in ways that are logical. Like, okay, all this code makes sense as a logical chunk. All this code makes sense as a logical chunk. Same with this one. One point at least of functions is to be able to separate and like turn this into one function call, turn this into another function call, turn this into a third function call. So you can very easily see what's happening just at a high level when you look at the main function. So that's our goal, and so let's make our own functions. So in order to do stuff like this, right, to just split stuff up, not make main do everything, have main start delegating, all right, just like we're using library functions. For that reason. But now we can make our own. Like, okay, maybe main can call function 1 that needs to call 2 other functions to do its own work. Like it needs to call function 2 and function 3, and we'll make all of these, right? And then maybe function 3, to get its job done, needs a little helper function called function 4. Like that's the kind of thing that we can do and have the interplay between all of the functions that we write. We can do it in any way we want and make as many functions as we want. All right, so here it is. Here's the secret. You actually know how to make a function already. Technically, you've been making the main function this whole time, right? That is a function definition. All right, so let's extrapolate. Let's see all the pieces. So the very first thing you say, like when you're making any function, is a type name. You give what's called the return type of your function. And I'll start labeling these with numbers. This is label number 1. So the return type is the very first thing you say. That's thing number 1. And that is your promise to give back something of this type by the time your function is finished with the return statement. All right. That's why it's called the return type. So we're returning an int. That's what main must do. All right. That's our promise. And then comes the name of the function. So that's part 2, I guess, thing number 2. And then in between your parentheses, you put not arguments. They're not called arguments in the definition. They're called parameters, right? So that's thing number 3. Those are called function parameters. We don't call them arguments in the definition. The arguments get passed into these variables called parameters. We declare what we want. Like this needs to be this needs to be that next. All right, and those are our parameters. And then we give our curly braces and have a body and have like, what do we want to do given those parameters? Well, it's all the code we would like to have run. So that's the body of the function, of course. And then finally, if your function has promised to return something of a given type, like an int, you must include a return statement somewhere. So here it is, like return. That's thing number 5. At least one of those. There better be a way by the time main is finished to have returned an int that we promised to return. Okay, so that's the secret. That's what it looks like to define any function. We can just change this up to make whichever ones we'd like. All right, so let's make the simplest function I can think of. Let's make one that just adds 2 numbers together, just does the equivalent of the plus symbol, just something very simple. But we'll go further than that soon. But here's the function that I want to write. Let's make a function called add that takes 2 numbers, 2 integers, x and y, and it gives back their sum as a third integer, because an int plus an int is still an int, right? And then we'll put some curly braces and we'll say what to do when we get those 2 numbers into x and y. So it's going to take 2 ints and it's going to give back their sum. So we're going to return their sum. All right, I hope that makes sense. So yeah, let me write that for you now. That's our very first function. Besides main functions, of course. So here it is, and first of all, you've seen stuff like this in the documentation. You know how this must be called and how it must be used. So let's just pretend we have it first. Let's think about what it's going to need, right? So like, we're going to call it like this, right? Its name is going to be add, and it's going to take 2 things, right? 2 ints. And so maybe we can just give those things 4 and 5. It's like that's how our function gets called, and it gives us back, right? It gives us back the sum of those two things, and we can use it in a larger context. Like we can multiply it by 2, shove it into a variable, just like give it to cout. Like that's how I want to use my function. And we're used to this kind of syntax from the documentation pages. So it's taken 2 ints, gives back a third int. It's like these are the ways I'd like to call my function, for example. Print 9, print 8. Okay? So now it's time to actually make the function. So just like we said, we say its return type, int, gives back an int. It's called add. It takes 2 things, and I'll call those 2 things x and y. You can call them a and b, whatever you like. And then our job in the body is to, using what we got, give back that int that we promised to give back. And so that's what the return statement. We say return, then we say what we want to give back. All right, it's got to be of the right type. And it looks like we only have one real option here. It's going to be, our job, right, is to return, or give back. That is return the sum, right? The sum of x and y. That's the whole point. So like if this was 4, 5, we should sum together the x and y. In that case, it'll make 9. Okay, x and y will be 4 and 5. That's the goal. Return x plus y. That's it. So this function gives something back. We said it's returning an int, and we did that here. So it's just a one-line body, really. And it does exactly what we would expect. So when you call a function, the for, this argument is being passed into this parameter, we say. This argument is being passed into this parameter. So x and y, for a split second, as this is being called, are set to 4 and 5 here. Same with this one. For the second call, x is going to be set to 1, and y is going to be set to 7. So in general, when you call a function, like you said add, like with 2 things, a and b or whatever, like this is where you called the function. What that means when you call a function, it's really just saying like go run the body of the function with your parameters set to the arguments, right? So that's essentially what you're shouting out to C++ when you call it your function. So it's saying run the body of the function I cannot write letters today, with, because it needed 2 arguments, right? Add takes 2 things, and there's going to be set into things called x and y. So set x with x equal to the first thing, so the a, and y equal to the second thing, the b. Okay? Does that make sense? That's what's happening when you call a function. It's like, all right, go run the body now. Here are the 2 things I want to be plugged in for x and y, just like here. Go run the body of add now with 4 and 5 plugged in for x and y. That's what's going to happen. Okay, so that's the first thing I want to tell you. The second thing I want to tell you is C++ is pretty nice. It lets us do what's called overloading of functions. So we can actually have a bunch of different add functions. They can all be called add as long as they take different things and like give back a different thing. So then it's not ambiguous which one is being called. So I'm going to make a bunch more functions called add that like works on doubles or strings, or whatever you want to give it, that where adding makes sense. Right? You can have a bunch of functions with the same name as long as it's not ambiguous which one you're calling. And so when the types are different, for example, that's not ambiguous anymore. So here, let's have some more adds. Let's be like an add that works on doubles, right? It takes 2 doubles, x and y, and it returns their sum still with the plus. It's still going to work, right? Same with strings. We can make a string function for adding together 2 strings. That's a thing that makes sense still, right? String add takes 2 strings, uses the plus operation on them to add them together. Yeah, it's like that's a possibility. We can be doing that. And then I can call them. I can call them with the same name. It's still called add. Down here, I can say, all right, cout add together 3.14 and 5.67. And the idea is C++ will notice that you're calling this with doubles, and it's like, all right, which of these add functions did you want to call? It must have been this one. Okay, and it'll give you your double back. That's what's going to happen. All right, so let me show you that one, and then I'll show you a string example too. There it is. Apparently that's the answer. Then we can do the same for strings. Just for fun, we'll do it separately. S1 equals high space, and then string S2 equals mom exclamation point, and then we'll see out the sum of, or the add function result of S1 and S2. So yeah, these arguments can be other variables. It's just like S1 is going to be plugged in for X when it's getting called, and S2 is going to be plugged in for Y when it's being called. So these are the arguments. These are the parameters, we say. And it's going to work. It'll notice that, okay, you're calling this with strings. Obviously, you did not want the double add function or the int add function. It notices that you want the string add function, and it calls this one. It gives you back a third string. Okay, I think that's what I wanted to say there. So these are all examples of functions that take 2 arguments. And so you need 2 parameters to get those 2 arguments, and they give back some value of the same type. All right, that's a function that adds 2 things. Cool, simple. Let's write another simple function. Let's make a function that prints out hello whenever we call it. All right, and this function, it's like we call it and it prints hello. So first of all, it takes nothing, right? You just say print hello, and we know that it will do its one job of printing hello to the screen. And then also, like, it just goes off and does the work for you, right? It'll call cout for you. You just put it on a line by itself. So this is an example of a function that does not need to give back anything. It does not need an int or a double or a string here. There's nothing for this function to give back because we never use it in that context. We never like try to multiply the result by 2 or anything. This function just is called by itself, so it doesn't need to give anything back. What do we put as our return type in that case? Because you always need a return type. So there's a special one, it's called void. Right? So void is the return type for when you give back nothing. It just means nothing. It's not a real type. So those are for functions that just go off and do something for us that are meant to be called on a line by themselves. All right. So let me show that to you. So it's going to be void print hello because you just call it by itself. It does not need to give anything back. So look a little different. So it's void print hello, takes nothing, so no parameters. And then what happens every time print hello should be called? It should print hello to the screen, right? Hello, and then a new line. And then I can go and I can call it in main. Yeah, so print hello. Bam. So there it is, just on a line by itself. See the difference? Add needs to be called like this. Print hello needs to be called like this. Boop. And so there's the hello. Lovely. And yeah, one of the nice features of functions, as well as just being able to package code up together in a logical place, is that you can reuse your functions as much as you'd want. So I think I did that for the int add function. I called it twice, but like any of your functions, you can call it as many times as you like, call it in a loop. Like that's the beauty of functions. So here I called it 3 times. So it's going to go print hello 3 times. That's really nice. And so it saves thought. It's like, all right, I understand what's going to go on here and what's going to happen. Cool. So yeah, that's functions in a nutshell. Some functions give something back, some functions do not give something back, and there is a big difference, and I'll get into that explanation some more soon. All right. So yeah, in general, now we can talk about this in extreme detail now that we know both sides. Let's go back to what it means to call a function. All right. So here I am calling my add function, for example. Again, you know what to do, right? When you're calling a function, you got to say its name. That's thing 1. You have to pass arguments. That'll be thing 2 between parentheses. Whatever the function takes, as many parameters as it has, it's going to need arguments for all of them. And if your function gives something back, you need to use it in some way. You need to use the result that this results in. If it gives something back, if there is a return value, you better use it somehow. So that's like thing 3. Shove it in a variable, cout it, do some math, and then put it in a variable, stuff like that. So use the return value if there is one. Otherwise, just call it. And yeah, the last piece of the story that now you can understand, what I've been saying is like the second you call your function, what it does is it goes and it jumps up to the body of that function. So like add int x, int y, and then you had your body. So it jumps up to the body of the function, having set the arguments into the parameters first. So for the duration of this call, when we hit the body of add and it starts running, then x is going to be set to this a, and y is going to be set to this b. So in general, when you call a function, the parameters from your definition, they are taken what you give it as arguments. They're taking the arguments from the call site, we say. All right, that's the last piece of the puzzle. That's the full story now. All right, so that's what's going on, and I hope that makes sense. So yeah, I gave you a few examples of each kind of those functions, and the return type kind of tells you how you need to call it. All right, so here is an example for you to make sure that you're getting things. So here is a function. I called it 5, And the goal of this function, or the goal of this function is to do something about 5, right? And then here in my main function, I'm calling 5 and multiplying it by 2. So I think my goal is to print 10, all right? That's the goal of this program, is to print 10, but something is horribly wrong and also subtly wrong. Do you see it? So think about it. Pause the video, please. That's how you learn. There's something wrong with this code right now, and it's not the fact, like, pretend that IOStream and everything normal is up here. Just with this particular part of it, these two pieces, there is something horribly wrong. It's not going to print 10 like I think it should. All right, so think about it, and we'll come back. All right, do you see it? So again, void, remember, is meant for functions that don't give anything back. So this, what does this function do whenever you call 5? It just prints 5, doesn't it? Just prints 5. Does it give anything back? No, it's void. It prints 5 to the screen. It never gives it back to the person who called you. All right, and this is the reason I'm having this slide and this question, is for you to notice this, because it's a very common mistake that I see among CSCI 40 students. So we have been used to like printing all day long, and printing and returning are completely different things. Like this function should have returned 5 if you want to use it in a larger place. In CSCI 40, we've used printing for everything, and so we think that printing means giving it back, but no, it means putting it on the screen. All right, so there is a big difference, and yeah, let's talk about that. So what should have happened if you wanted this to work, like to be able to be used in a larger context like this is going to get replaced with nothingness because it gives back nothing. Instead of printing 5 here, what this 5 function should have done is returned 5. Does that make sense? So it should have been called int5, first of all, and then it should have said return 5. That's how it gives it back to whoever called you. And that's where you can like pretend it got replaced, and this can be replaced with 5 in that sense, and then it will make 10 and do it right. All right, so that's the idea. So these two functions are not equal to each other. This is what it should have been. Does that make sense? So let's pretend that like this would compile. This won't even compile, first of all. I encourage you to try it. Like, what would happen if this was even allowed? So let's talk about it. Here's your terminal screen. Let's pretend this is the terminal screen. You run the program. So the first thing it'll do is it'll get to this line. It's like, all right, I need to see out something. And so see out sees that it needs to see out whatever this is. And it's like, all right, I need to see out 5, the function call, its result times 2. So I better go off and call 5 to get its result. So I can multiply that by 2. So it goes off and it calls 5. And then 5 is like, all right, I'm going to print 5. That's my job. That's what it does. So it's going to print 5. And then it will return back to the person who called us, having given back nothing. So this essentially becomes the emptiness, the void. And see how it's like, all right, I got back nothing. I need to somehow multiply that by 2 and print the answer. So that's just impossible, right? So it's like, what do I do now? Crash the program. So this doesn't even compile. You can try, and it's like, I don't know how to multiply void by 2 is what it will say. So yeah, that's the difference between printing and returning. I have a slide on this. All right, so this is a big deal. This is a very common error. All right, so I want to hit it hard. So let's see here. How do I want to talk about this? Yeah, so here are 2 functions. Here are 2 functions. This one gives back a value. This one returns stuff, right? And then this one does not give back a value. It just goes off and does stuff. The question that you should be asking whenever you see a function made for you is, how can you use it? How can you use these functions in main based on their types? Okay, so add, for example, you see that it's going to take 2 things and give you back a 3rd thing. All right, so if you want to use it, you better call it like this. Like, you got to give it 2 ints, of course, 3, 4. And then once you use it, you can pretend, essentially, because it's returning an answer, you can pretend that its return value is going to replace your call to it. It's like, it's as if you just said 7, essentially, whenever you call it like this. And then, all right, how would you use 7 in a program? It's like, you can do some math on it, shove the answer into a variable, something like that. So that's how you could use the add function. Does that make sense? Alternatively, you could see out the result of the add function, add 5, 6, something like that, and then a new line, of course. That'll also work. You just could pretend, right, when this gets called, it's going to be replaced with its return value, so it's as if you said see out 11. That's what's going to happen. It's going to go and do the work for you. How can you not use add in main? You can't do it like this, can you? You can say this, right? Add 2, 3, semicolon, and this will do absolutely nothing at all, won't it? because like it's never going to print anything. It's just going to return the answer. This is not going to do anything for you. It's as if you said, because it returns 5, right? It's as if you said on a line by itself 5 semicolon. That makes no sense at all, does it? It's just making the computer warm by doing the work for you. It gives back the answer, and then nobody took the answer to do anything with it. So you better use the answer for a function that returns something, all right? And then print hello is the opposite side of that coin. So how can you use print hello in main? You have to just call it on a line by itself because it gives nothing back. Print hello, parentheses, semicolon. It's done, all right? What you can't do is anything where you use this in a larger context. You can't be like, all right, let me see out the result of calling print hello. Does that make sense? This will not do anything normal because it's going to go off and like, all right, I need to call this function, get a result back so I can print that result. So it goes off and it calls and it prints hello, and then see how it's like, all right, I got back nothing. I got back nothing at all. I need to print nothingness. I need to print the void. So that was wrong. Okay. So yeah, just pretend when you have a function that returns something, pretend that it's going to get replaced with its return value. That's the goal here. And that kind of hints at why void functions must only be called on lines by themselves. They cannot be used in a larger place because once you replace it and try to print nothing to see out, that makes no sense at all. Okay, so let's make some programs, or let's make a new program to talk about that further. You may be rolling your eyes right now, but I know it's a hard concept for CSCI 40 students, and I want to spend some time on it so that you don't make the mistake that I see a lot of students making. So, all right, let me just copy in the add and the print hello. I guess I already have it. Let's get it from here. So here's print hello, boop, and then let's do the int add. Cool. So yeah, let me just re-explain what I said and I'll show you it running. So like add, this is the add function. You call it like this, and you can use it in a larger context because you get to assume that this call, right, is going to give you back the result. It really will. It's going to return back the answer. It's as if essentially you said 9. It'll do the work for you. All right, it'll make 18 and print the 18. So that's the goal. That's how you use that one. And then print hello, you just say on a line by itself because it goes off and does something for you, and there's nothing that it gives you back. Yay, so it does exactly what you'd expect for both of those. All right, so let me show you the wrong way for each of them. So first of all, print hello, you can't do this. This makes no sense. And I hope you see why. It won't even compile by trying to do that. And you're going to get a weird long error because C++ is sometimes unhappy with these things. So if you scroll up to the top, when you get a long error like this, usually the first thing it says to you is the real problem. So here it's trying to do its best and tell you, of course it went away when I used my mouse, sorry. What it's trying to tell you is print hello results in nothing. And it's like, you just gave nothing to see out. I don't know how to print nothing. So that's essentially what it's trying to tell you here. So that's the problem. And we can't have that, all right? This one, this is like how you shouldn't be calling add, right? This is on a line by itself. It's just like making the computer hot. It's as if you said 9 semicolon, right? And this is allowed. You can actually do this if you really want to. If your function does something else and like it makes sense even if it returns something to call it on a line by itself and just throw away the answer. But add, it makes no sense to do this. It will compile and run. But it will just make the computer warm. It will do a little bit of extra work and you'll never see the fruit of that labor. It's as if you said 9 semicolon. That does nothing at all. Okay, computes the answer, throws away the answer. So yeah, that's how you can use and not use these kinds of functions. Functions that return stuff and functions that don't return stuff. All right, I hope that makes sense. Please yell at me if you have any questions about this. This is just a very common error that I see and I did want to spend some time on it. All right. But I think that's all that I really want to tell you about making functions. Now I just want to give you examples, all right? The more examples I give you, the more it'll make sense. So just in general, we have some really good tools now to break down problems with. Functions are like amazing, an amazing way to make it easier to think about a problem because we can break it down into like ideas of functions and then go worry about how to make those functions later. So that's a huge, huge deal. Let's learn how to like create algorithms, all right? So here is a silly example for you. Here's the problem that I'm going to throw at you. All right, so here's the running example for a while. let's say that I give you this question, like how can I sum up the squares of the numbers 1, 2, 3, all the way to some value n that maybe the user gives me. And that's your problem. I want you to make a program that does that. A program that sums the squares of the numbers 1, 2, 3, 4, all the way to n, whatever n is. So for example, if n is equal to 3, then your job is to sum together, then sum up 1 squared plus 2 squared plus all the way to 3 squared, right? And that's going to be equal to what? 1 plus 4 plus 9, so 10, 14. All right, so that's what you calculate if n is 3, and you want it to work for any n, any normal n that's at least 1. All right, so that's your question, and all right, you go off and like if that's your boss giving you that job, that work to do, you're like, all right, I'm going to write an algorithm to solve this problem. I'm going to make it work, and then you have to somehow break it down. All right, so this is my job now. I want to teach you how to break down problems, just in general. All right, so it's like, I know I'll make an algorithm to do this, but we have to like zoom out and think about like, all right, how do we even make the algorithm in the first place? So just in general, remember that algorithm, just the word, means it's a sequence of steps to solve a problem. So it's like a recipe. And yeah, my goal is to teach you now how to break down big problems into smaller pieces. I've been teaching you that, but functions give us a huge new thing, a huge new thing in our arsenal to throw at problems. So yeah, I want to teach you how to make a bunch of little mini algorithms and how to hook them together to do the right thing. All right, keep going until the pieces are so small it's just obvious what the answer should be for each of them. So like you give, like maybe I give you this initial thing and you realize that, okay, I could break this down into this part and then this part, and then depending on what the answer is, either I go off and I do this thing or this thing, and like that's your program. Like you think of it at that kind of high level. That's what I want to teach you. All right, so I'll give you examples to teach that. You just keep on going and do the breaking down process until it's not scary anymore. That's the beauty. That's the beauty of functions and breaking down these things with them. So a huge goal right now for you, that I have for you, is I have been giving you very detailed instructions, especially in your labs. All right, I've given you a lot of fix-me's and stuff like that. It's now my job to start giving you less and less instructions. All right, I'm going to give you like descriptions of the answer that I want to see from now on, and then you're going to go off and figure out how to break down the problem in the way that produces the answer. All right, that's the way that you learn. That's what I have to start doing with you now. All right, be ready, mentally prepare. And so just in general, like when you're programming, what you're going to do, this is kind of the process that I want you to think of it, think of a problem with. So it's like you read your problem statement, then you figure out like, all right, figure out what its input is going to be, like what is this problem going to take, and then like what is its output going to be, and then go off and implement it. Take the input into the output. All right. And you'll have to test and like fix bugs, so debug until it works. And a good way to debug is to print out intermediate answers with, for example, cout. Okay, so all right, let's go through this example now. Let's break down this problem. So this is our problem. I want to sum up the squares of the numbers 1 through n, 1, 2, 3, all the way to n. So the very first thing you should do when you see this problem is like, all right, what are the pieces of it? What are the pieces of this problem? How can I break it down? What are the smallest things? So if you stare at this long enough, I think you will see that there are 3 main pieces of this problem, right? I need to sum up stuff, I need to be able to square stuff, and then I also need to be able to enumerate numbers 1 through n. Do you see how those are kind of the 3 key pieces of this problem? All right, if you don't see it, that's okay. Just come back with more examples. It'll make more sense the more examples I do. Come back to this problem. But those are the pieces. And then the next thing is like, all right, how is the information going to flow through the pieces? All right, how's this program when I eventually make it? How's it going to like play out? So I hope you see that it's kind of backwards. The problem statement is talking about the problem that you need to do backwards, isn't it? So like you need these numbers first, right? You need to create those numbers, because then only once you have them can you square them, and then only once you've squared them all can you sum them up. Do you see that the problem statement in English is a little bit backwards? This is thing 1. I need this first. I need these first. Does that make sense? And that's the kind of stuff that I want you to figure out on your own soon. All right, and then you take that and like you feed those numbers into your squaring functionality. That's thing 2. And then you take those squared numbers and then you feed them into your summing functionality. That's step 3, and then that will give you your final answer. Do you see that? That's the flow of data. Like, that's telling you what has to happen before some other thing. Okay, so that's a good breaking down of the problem. Now let's start writing a program to solve it. All right, and so I want to teach you something called stubs. So it's a kind of function. A stub is a function that just compiles but doesn't actually work correctly yet. So the first thing we're going to do is write a bunch of stubs before we get into the real code. All right, so our final function, I'm going to call it this: sum squares from 1 to. All right, that's going to take a number n, right, and it'll go off and solve our problem. All right, that's our goal right now. But I'm going to write a stub for it first. It's just a function that gives back a silly answer. As long as it's just going to make it compile. As long as it returns the right type, it'll be happy, but it's going to be incorrect. So let's make a stub for our sum of squares problem, and that's going to allow us to get just the scaffolding ready to solve the real deal. All right, so a stub is just a function that gives back a silly answer right now. So let's stub out our answer for this sum of squares problem. All right, so yeah, let's say that, like, here's my function. It's called sum squares from 1 to. It's meant to, right? It's meant to take a number, an int, right, int n, and go up to that. And its job is to return what, right? What will it be returning? Well, the sum of the squares of a bunch of whole numbers, right? The sum of the squares of a bunch of whole numbers is still a whole number, so it's going to return back an int. You see that? So that's going to be the return type of this function, int. Cool. And then we need to give it a body. We'll get to that in a second. So what I mean by stub is give this the simplest body possible to make it compile. Make it incorrect, though. All right? That's what it means to be a stub. So I'll just say return 42. Does that make sense? I'm just going to say that right now. Do you see how this will compile, but it's completely wrong? That's perfect. I can get the scaffolding ready. All right? Just pretend that it works right now. Let's do the rest now. All right, so like the goal is we want to call this with maybe whatever the user gives us. So like let's set up the scaffolding. Let's like ask the user to like give us a number. Cout enter n, and then I'll get that from them. Make room for it. Get it? And then like, all right, how do we use our function to solve the problem? It's just like, all right, go off and call it. Sum squares from 1 to n. These are 2 separate n's, by the way. It's like this is going to pass our main n into this n parameter. All right, we'll talk more about that later. But that's how it works. It'll go off, give you back the answer, and then you print that answer. Okay, so that's like the full story. That's the scaffolding, and it's ready. All right, so no matter what the number you give now, it's just always going to say that the sum is 42, but that's okay. 5, 42. 3 is 42. It's always 42. Okay, but that's a stub. All right. That's an example of a stub. It helped us just get everything else working. Now we're ready to come back to it and really solve it. Okay, let's see now. Now our job is to write the real implementation and like do the pieces. And we could separate all these pieces into separate functions. That's going to be the goal. All right. So here, our jobs, right, are to enumerate 1 through n. So like we're going to have to loop through these numbers essentially. That is what must happen. And so let's just put that enumeration loop in the main sum squares from 1 to function. That'll be perfect. And then we need the ability to like square numbers, right? Square numbers and then also sum them up. So I know we can use just plus, but I'm going to give you examples of using functions today, right? So we're going to use too many functions even. So we can use our add function to sum stuff for fun. You never do that in real life, you just use plus, but still. And then we'll make a square function. That's going to be useful too. You see how if you just call it, it's immediately, you can tell that like, okay, yeah, that's going to square the number that we give it. So square should take a number and give you back its square. So int takes an int, returns an int. So that's going to be the process, okay? Let me do that for you. So let's steal the add function because we have that already. Whee! So there's that one. And what else? Let's make the square function. That one's easy. We don't have to go to stubs there. Let's just like immediately make it. So square takes some number, I'll call it x, and it's supposed to give back the square of that number x. So like, what do I return? X times x. Beautiful. So those are those 2 functions, and now let's use them in this one. All right, so sum squares from 1 to, let's just loop from 1 to n, enumerate all the values, and I'm going to have to keep track of a sum as well. So make room for a sum, and then start looping. So for int I equals 1, I is less than or equal to n, I plus plus, that'll loop through all the right values. And I would like to set sum equal to whatever it was plus like all the squared values, right? So the first I squared, the second I squared, 1 squared, 2 squared, 3 squared as I is ranging, so square I. All right, and even this plus, we can turn that into a call to our add function, can't we? So add, just for fun, add sum into square, just to get practice calling our functions. That's it, okay? You see how it's going to keep sum getting bigger. It's going to add in the new value of I, the 1, the 2, the 3, having squared it first. So it's going to add in the 1 squared, the 2 squared, the 3 squared into the sum variable. Excuse me. So yeah, now our job, like we've computed the answer. Now our job is always, right, because this returns in it, we have to give back the answer with return. So return sum, semicolon, and that should do it. That should go off and call everything correctly. What was our example one? It was 3, right? So if I say it with 3, it should be 14. Let's test it out, see if it's working. Hey, there we go, nice. So there we got our 14. Any other values? Apparently with 4 it's 30, with which is 5, it's 55. Cool. So yeah, that seems to be working. You can go off and use a calculator to confirm that, but that's a good example of breaking down problems. You'll probably never make an add function. That's kind of unnecessary, but a square function makes a lot of sense, right? Just as you read it, it's very clear to see like that this is going to square the number that we give it, and that's useful for us when we look back at our programs that we've written. Okay, so I think that's what I wanted to say there. What else? So yeah, let me next talk about how to clean this up a little bit. All right, so we can make this look a little bit prettier by declaring functions above main and then defining them below, just promising to implement them and then defining them later. So usually, well, I guess most times at least, when you look at a program, you're going to go straight for the main function, aren't you? Because like that's where it starts, that's what it's really going to do. It doesn't really matter yet that you know what the functions do, okay? So wouldn't it be nice to have main at the top and then have your other functions below, because they're like, main is the star of the show, these are all the supporting cast members essentially. So that's what we'd like to be able to do. We'd like to be able to like take all these helper functions that we're using in main and stick them below so that when you open up the file, what you see first is main. All right. Sadly, you can't do that just by itself because it's going to complain and give me an error and say like, I don't know what sum squares for 1, 2 is, because the silly compiler can't look ahead in the file and notice that it's there. So other languages have solved this problem, but C++ has not. So you need to tell C++ that this function exists before you try to call it. You don't have to give the definition, but you have to give a declaration. All right, so here's what it looks like. Here's like a definition of a foo function, like it takes init, returns init, and it gives the body. You can declare that, just promise that it will eventually exist by doing this, by just getting rid of, copying and pasting it, getting rid of the body, and putting a semicolon. This is a declaration of a function, all right, of that same function, foo. So this is a function declaration or decl, and then this is a function implementation. I guess we can abbreviate that as impl, all right? So there we go, that's the difference. And so you can put this at the top just to promise to C++, give it like an IOU, like I will eventually make this function, here's its return type, here's all you need to know in order to call it. You'll eventually get the code. That's your promise whenever you make whenever you do that. So I'll say that, semicolon. Technically that's the only one I have to use, because all the other ones, like, this is the one that's calling sum and add and square, right? And like, those both are implemented above it. So technically this is the only one to get this to compile that you have to put up here, but it's common to just put all the ones you got up at the top for fun. And do you see, like, you open this file, it's like, all right, I know that these functions exist. Here I am defining them later. And then you see the star of the show first. There's main, and like the rest of the code is below. So it's declare. You put your declarations up here, then you can implement them later, as long as you eventually implement them. These are function declarations. They're just IOUs. They're promises to eventually make those things, and that's all C++ needs in order to call the stuff. And it's like, all right, I'll figure out the rest later. So yeah, it still works. Enter n3, I still get my answer. Okay, so that's declaring functions, and then these are implementations now down here. All right, so you're able to move them like that if you'd like. That's just good style. And then, yeah, I think the final section of today's lecture is on testing. All right, so I want to hit this hard because this is a very common thing in industry. Everybody cares about knowing that our programs that we write are correct in some way. So like, how do you know? How do you know that your function that you wrote, for example, was a correct function? Like, how do I know beyond a shadow of a doubt that this sum squares from 1, 2 is always going to work? I just try examples is what I've been doing, but there's a better way. All right, so like it'd be nice to know that everything we ever write will always work, no matter what input we give it. That's very, very intractable, though, even with just a function that takes an int, right? Because in order to test this function, there are like 4 billion-ish ints. You have to give, like, you'd have to type in each one of those. You could try to automate it, I guess. And you have to like do the math on your own end and make sure like what it gives you back was the same as like what it should have been if you did it on a calculator or something, if you did it manually. So that would take forever, right? Just try every 4 billion ints. Run your program, do the math yourself on paper, see if it all lines up. Like if you tried every int, then you would be 100% confident that this function worked, right? And this gets horrible, right? With more arguments with different types. Like maybe you had a 2-argument function, then you have a bunch of different pairs of every int that you'd have to check. That's just completely not feasible. So there is a middle ground, though. What people tend to do to test their functions is they write things called unit tests. They come up with some good numbers to try to run our function on, and with enough of good numbers, it will, like, if your tests pass at least with those few numbers that you give as your unit tests, then you can be pretty confident that it's always going to work. All right. There is a way to actually prove that your program is correct beyond a shadow of a doubt. Like, you'd have to use math, though, and you'll have to wait till CSCI 26 to learn about that. But yeah, we're going to do things called unit tests. So just take a few things and check them, see if it works. All right, so unit testing in general, unit just means a small chunk. So what you do is you pick a tiny piece of your program, usually it's at the level of a function, and you write a bunch of test cases for that little piece, for that little function. So you call it with a bunch of different values, and you pick your values very carefully, though. They have to somehow make sure that like it's going to work. All right, so let's test a factorial function. All right, I think that's a good example. So let's make it first. So first of all, do we know what factorial is? Factorial is this exclamation point in math. It's like 5 factorial is supposed to be 5 times 4 times 3 times 2 times 1. That's what factorial is. It's going to, like, all right, what is it going to return? A factorial is always of a whole number, right? So it should be returning a whole number back to us. So factorial always returns an int. Is there a parameter to our factorial function that we're about to write? Yes, for sure. We need to know what number we want to take the factorial of. That's all. So one parameter, its type is an int. You can only take a factorial of whole numbers. So it's going to take an int, return an int. All right. We'll call it factorial. And now we have everything we need to go off and start it. I spelled it wrong. Factorial. There we go. All right, let's make a stub first. All right. So, let's see here. I guess I want to make a new file. Yeah, let's make a new file. I'll call it testing. And I would like to make a factorial function. Int factorial takes a number, let's call that number n, and then its job is to return the factorial of that number n. Let's see here. And then I'll put just some random number like return 42 in here for my stub implementation. All right, so this is completely incorrect right now. So that's perfect. That's the start of my factorial function. And now my goal is to write a bunch of test cases. All right, test cases for the function that I'm trying to make sure is correct. All right, so it's usually a good idea to write the tests even before you write the implementation because they'll help guide the implementation. So yeah, just in general, a test case is, at the end of the day, it's like an if statement. It's just a Boolean expression. It's either true or false. It's going to give back true if it worked, false if it didn't. It's going to compare like what you expected your function to give back with what it actually gave back. That's what a test case is. All right, so yeah, Boolean expression, remember that word, just has to do with true or false. A Boolean expression is something in C++ that gives back true or false. So it's like a relational operation. Gives back true/false. That's what that is. And so let's write some tests just using if statements, because that's one place you can put your Boolean expressions. And I'm going to translate it to an industry standard function called assert true that I'll talk about. All right. So let's make some tests for our factorial function. I know it's not correct right now, but let's see here. Let's be like, all right, let's call factorial and be like, you know, I know that the factorial of 3, that could be my test case. That could be my first test case. I know the factorial of 3 is equal to 3 times 2 times 1, which is 6, right? So I can make sure that that is true by comparing it to 6. Does that make sense? This will be what it gives back, the actual call to it, and this is the number that it should have been as an answer. So I can just do that in an if statement, make sure that is what I see here. So if the factorial of 3 is actually giving back 6 and it was equal to it, that's the right answer, and so it passed the test. Does that make sense? That's your unit test. That's 1. It's like passed. Or people usually do it like that. Passed. Factorial of 3. Now I know it passed. Cool. And then I guess a new line 2. Else, right? If that wasn't true, it failed. Failed the test. Does that make sense? So that's a test case. It's like you're comparing, like you have an idea in your mind. Let's try factorial of 3. That's my test. So call your function, have it give back its answer, and make sure it was equal to the answer that it should have been. That's all the test case is. And we can do the same for other ones. And be like, all right, let's try factorial of 4. That's supposed to equal, I guess, 6 times 4 then, right? So that's 24. So it should have been 24. And if it was equal, it passed. If it wasn't, it failed. So let's compile and run. Boop. Cool, so they both failed right now because it's just a stub implementation, all right? And the importance of having multiple tests is because maybe your stub is sometimes right. Like you can hard code this to say 6, and had you not made that second test, you would be like, oh yeah, factorial works. Does that make sense? So the more tests, the better, for sure. But yeah, let's do it right so that all the tests pass. Okay? So how do you implement factorial for real? I guess we have to loop, right? Loop through all the numbers. It's like it's going up to 5. Got to loop through 5 all the way down to 1. I guess we can go all the way up as well, but I guess usually when you think about factorial, you start at the number, then you work your way down to 1, and you multiply everything. So like, let's write it like that. So I'm going to give back not a sum in factorial, but a product. And so I need to start my accumulator value at 1, because if it started at 0, you'd just be multiplying into 0, which is always 0. So, all right. Now I want to loop from n, right? If I want n factorial, that's equal to n times n minus 1 times n minus 2, all the way down to 1. So start at n, and I equals n. Keep going while it's greater than or equal to 1. I minus minus. I'm sorry, it's not n minus, it's I, right? I'm using I. And then, yeah, I just want to multiply into the product variable. So product equals the product of itself with this new value I. All right, so that'll, like, if it was 5, n was 5, it would go start at, multiply 5 into product, 4 into product, 3 into product, because it's going minus minus. All right, and then by the time it's finished, it's put the right answer into product, and I can return that. I hope that makes sense. And so that's going to mostly do it, right? That's going to pass our 2 tests. Does that make sense? These are my 2 tests. Now it's passing, like what I expected to see is there for both of these calls. It's given back the right thing. So I have a decent amount of confidence that factorial is right. That's pretty cool, right? That's what it means to test stuff. So instead of using if statements, people tend to, like, you see that these 2 tests look very similar. That should scream, I should take the similarity stuff and put it into a function, package it into a function instead. All right, so that's what we're going to do. So people tend to use what's called assert true. That's a function name that's going to make up our test. All right, so let's pick out what's common in between these 2 things and make a function called assert true that does that. So here, boop. I'll copy that for later. So it's called assert true, and we'll figure out what's going to take in a second. But like, do you see like what's in common between the factorial 3 and factorial 4 question test? It's like you're always like comparing one side to some other side. Like if something's equal, something's not equal, you do a comparison, and then you say passed, and then like the name of your test, right? So that's where we should put variables. I hope that makes sense. That's where we should put variables. So even like, we just want to make sure something's true. So honestly, we just put something here, something that is a Boolean expression. So that becomes 2 arguments essentially. So we're going to have, essentially the user is going to give us some Boolean that they expect to be true, and then also a description of what the test is. Do you see how that's going to correctly, if we had both of those things, it would like, that's what's in common between the two of these. Is like, all right, we're checking a Boolean expression. If it's true, we say that it passed. Otherwise, we say that it failed. Cool. And so that means what assert true is going to take is going to take a Boolean, bool b, and string description. And so I need strings. Whee! And then I guess it does nothing. It doesn't return anything, right? It just prints passed or failed. So it's going to be a void function. That's what assert true is. And so now instead of, this is what is commonly used in industry when you're doing your unit tests. So instead of doing it like this, let's change our tests to work in the new style using assert true here. What I'll do is I'll make a little split screen so that you can see what assert true is up here, and then here I am in main. I just scroll down. Here I'm going to call assert true now. So I will say, like, to make these tests work using assert true, what I do is I say assert true on a line by itself because it's void, and then I give the Boolean that I want to assert to be true. It's just whatever I put in the if statement, right? Because that's what it's going to go and check. So I want to assert that this is true, that the factorial of 3 gives back 6, and then you give some word, some name to describe it, okay? So that's the goal. Let's see, actually it's probably better if I split this way, huh? So there's assert true, and then here's down in main me using assert true. So assert true, the factorial of 3 is equal to 6, and the string that describes that test can just be like factorial of 3. All right, so that's a call to assert true, and then same with the other test. That'll be called factorial of 4. Does that make sense? So that's a very quick one-line way to make a test. It's like, all right, give what you want to check. What do you assert to be true? What should be true right now? I'll go and make sure that it's true, and say passed or failed, depending. And what do you know? Does the exact same thing. Nice. So that's what assert true is all about. I hope that makes sense. And you can have as many tests as you'd like, just enough to convince yourself that factorial works. A good rule of thumb is that you do want to be pretty thorough as you can possibly be. You want to make sure that your unit tests, what's called, cover the code. All right? So they should cover the code, and what that means is you want to make sure that every piece of code, every line of your factorial function, by some test is being run. So like maybe you have an if statement, you have 2 branches, you got to make a test that goes down one side of the branch and a test that goes down the other side of the branch. Stuff like that. That's what it means to cover the code. All right, so let me write that down. So it's like check that all the lines are being run in some test at least. Check that all lines are hit. Check like corner cases, places where you expect to see things work a little weird, corner cases, also called edge cases, etc. So that's the goal, all right? And then a good example of like covering code is like if you have an if-else statement, you know that only one side of the if-else is ever going to run, so you better have two different tests, one that hits the if side, the true branch, in your function that you're testing, and one that hits the false side, the else branch. Does that make sense? So that's what it means to cover your code. And just like make sure that you're trying every different kind of input that's gonna, like if you have a loop, for example, make sure you add some inputs that check corner or edge cases where like do you come up with an input that skips the loop, come up with an input that runs the loop only one time, stuff like that. Does that make sense? Like those are good corner cases. So like a good example of a test that would check, or that would never run, right, would be something like the factorial of 0, right? that would skip over this entire loop, wouldn't it? The factorial is, if you call this was 0 right now, it would skip over the loop, and what would it do, right? Because 0 is not greater than or equal to 1. Like, all right, factorial of 0, what should that give back is now the question. Do you see how thinking about the tests helps you make the right choices for your program? And so it just so happens to be that in math, the factorial of 0 is defined to be 1, all right? And so it also just so happens that given this implementation, by skipping the loop, it just returns what was ever initially in product, which is also 1. So it actually just works out, but factorial of 0 will be happy. But that's a good test to have because it skips the loop. Does that make sense? That's an edge case for sure. And then have a test that only runs the loop body once. Make sure that if it does it just once, it's still fine. The factorial of 1 is also defined to just be 1, okay? So the factorial of 1 is correctly giving back 1 right now, so stuff like that. All right, that's going to help you check edge cases. There's one last edge case that I have not talked about. Do you see it? I need one more test here for sure. What else could I give? Negative numbers, right? The factorial of negative numbers doesn't even exist, and that's something you should be thinking about. Like, what should this give back right now? I'm not sure. Question mark. Who knows? What's it going to do right now is now the question. You can like print it out. It'll just like 0, it'll skip the loop and give back 1, which still doesn't make sense, right? The factorial of a negative number doesn't exist. So do you see how thinking about the tests helps us come up with like, how should we actually program this? The factorial of negative 1, it does not exist. So we have to give back some value, right, that kind of indicates that in some way. So maybe let's make it so that if we ever give an invalid input to factorial, so like any negative number that's invalid, let's say that it always gives back negative 1 to indicate that it was just a bad input. All right, you could also like print out stuff as well, whatever you want to do, but like that's a good test. Does that make sense? That's us checking edge cases. Like, all right, which values should factorial even accept right now? See that? That's important. So in order to get that working, to like return negative 1 if it's a bad value, we have to put something at the start here. You got to put an if statement. It's like if n is negative, then return negative 1. And so you can have a return statement anywhere. The second you see a return statement in your code, it's going to stop. So this will give back negative 1 immediately and get out of the function. It won't even try to go down here. I hope that makes sense. That's what's going to happen. So yeah, that's what factorial is all about. I think that should work now, our test. Boop. So, and that it's going to pass. It's going to give back negative 1. And then you just keep trying, like make as many tests as you think you need. Like factorial of 5 is supposed to be what? 120, is that? I think that's right. But that's enough. I think you can imagine, like, if you have some tests that run the loop 0 times, 1 time, check for corner cases, and then have some ones that run the loop like a couple times, you can be pretty confident that it's always going to work. And so I think I have all my tests passing right now, which is beautiful, and I think this is a decent amount. All right, and I hope you can kind of get a feeling for that too, based on what I've told you. So yeah, those are some test cases. I would like you to try now. So here is, let me give you assert true first of all. Here is what it takes to call assert true. Here's like the declaration-y part of it. This is what it takes to call assert true. Boop. I would like you to think about a test for this square function down below. So there's something wrong with this square function, by the way. Do you see it? It's not going to do the right thing always. So it's meant to take any double and give back the square of that value, again as a double. There is something wrong with the function. It's not always going to work. I'd like you to try to write a test case using this assert true to discover the problem. Write a test case that should have passed if the square was working, but will fail right now. Does that make sense? So give that a try. All right, did you see it? Did you see it? Let's see here. What do I want to do? So, dun dun dun. I don't think I want to go to code right now, do I? Yeah, let's just stay here. Do you see the problem? It has to do with some types. All right, so like square of right now. Do you see that the square of, if you call it with 1, it will give you back, what's it returning? it's always going to return the input. You see that? It's not even going to use this result on that first line. Subtle, right? So square of 1 returns 1, and that actually works right now. That's the only one that will work. But like square of 2, right? It should have been giving back 4, but do you see how right now it's going to give back 2? That's not good. So that can be your test. You can be like, all right, I want to assert true then. Assert true that if you call square of 2, it should be exactly equal to 4, right? And that can be like, your description can be, you just call it test or something, test 1, I don't know. Something like that. You see how that's something you can compare? This is one of those cases of do as I say, not as I do right now, because I am trying to compare a double right now to another double, essentially. So that's not good. You shouldn't be doing it like this. To compare doubles, you should be using subtraction, absolute value, and making sure the result is very small. Don't do it this way, all right? You should be comparing the right way, but that's the secret, all right? You pretend that I did it that way. It's just easier to write it like this. What you do is you're going to compare what you got back from your function to what it should have been, all right? And it's not going to work right now. It's going to fail. But really, you should have been comparing using double kind of comparisons. All right, so that's the first one. And then, let's see here. That's the first one. And then here is the second one. So here's another example. So let's say we fixed it up, all right? We're returning a better answer right now. There's still something wrong. Do you see it? So take some time, pause the video, see if you can figure it out this time. And write a test case to fail that should have passed. You see it now? So, all right, the key thing here is the fact that we're using doubles. If you say square of 2.0 right now, it should be giving back 4.0, right, as a double. It's going to give back 4, and that does work right now, won't it? But anything else will not. Anything in between, because of this type right here. Do you see it? Ints cannot hold decimals. So that was a mistake to put an int there. And so a good test case that will discover the problem is something like this, like 2.5. If you square 2.5, what's it going to give back? Well, it's going to do the right thing, right? It's going to put into squared number the answer. It's going to try at least. Squared num, that's my variable. It's going to set it to, well, it's going to try to put into it the right answer, which I believe is 6.25. But ints can't hold the 0.25, so it's going to chop it off and put just 6 in squared num. It's going to return back 6. You see that? That is not good. There's our error. And so that could now turn into a test. You want to assert true. Assert true the fact that your square of 2.5 should be giving back and be exactly equal to 6.25. But again, you should not compare doubles for exact equality. Do as I say, not as I do. So use the subtraction and the absolute value and checking that the answer is just really, really small. Okay? Remember that. But this is just easier for me to write right now. Test 2. Okay? So that's the secret. It's always compare what you got back for real. Like, what did square actually do for you? I'll give back 6, really. Compare that to what you really wanted. And remember for doubles not to do it this way. I'm being lazy. You should not be lazy. So, yeah, I think that's what I wanted to say. Let's see if there's anything else that I wanted to talk about. I think I showed you all the problems and gave you all the code I wanted to. So yeah, I think that's where I want to stop for the day. We started with functions. There's plenty more to talk about. There's plenty more where this came from, but this is where I want to stop. All right, so I will see you in the next one.